In this section, we're going to take a look at the concept of a Green's function. Whenever you're studying physical systems, there's two kinds of problems that are likely to arise. The first one we've seen several times already. Here I've given a second order example of one. Of course, it can exist in higher order or lower order, but just as an example, this is an initial value problem where you have an ordinary differential equation and you have some values of your function and its derivative at a common value. And remember, for an initial value problem, these must be the same. Their results can be different, but what you're plugging in must be the same. This is an example of an initial value problem. What we call the IVP. However, one thing you note here is that, again, these must be the same. What if they don't have to be? Well, that gives us a little more flexibility here in terms of our conditions, and this gives us a more general and somewhat more difficult problem. This is what's called the boundary value problem. Note that the boundary value problem is an ordinary differential equation. Right? It can be second order in this example, or it could be any other order. Here, however, if we ignore this second line down here, this is an initial value problem. You say, well, those look different. Yeah, but all this is really saying is right here, if I plug in this number into y, I get some number. If I plug in that same number into y prime, I get a different number. Well, these two numbers, they're just numbers. So if I multiply them by the right amount, say for example, each other but one with a negative and one with a positive, and then combine them, I get 0. So with just this first set of conditions, this is a different way of writing this, but even though it's different, it does mean the same thing. So with just this top part, this is an initial value problem. What makes it a boundary value problem is the fact that we add this line here. And notice that in this line, we have a different input here. This is not y and y prime at x naught. This is y and y prime at some other value. So with these additions, we now have a boundary value problem. Note that not all of these have to be defined simultaneously. It is possible that you maybe have this one is equal to 0, and maybe even this one's equal to 0. So you might get something like this and this as being some values. Okay? It's possible that all 4 exist. It's possible that maybe just 2 or 3 of them exist. And of course, if just those 2 exist, then you're back to the initial value problem. Okay? In all of these problems, whether you're looking at an initial value problem or a boundary value problem, what we have here, this f of x, this is called our input function. And when we talk about Green's functions, this input function will be of importance to us here. This is called the input function, regardless of which version of the problem you have. That's what we're going to go ahead and call it in this course. However, there are other names for this, depending on what book you're reading or who your professor is. These are also sometimes called forcing functions. It's the same thing. I don't know how to spell. Let's try that again. Forcing functions. When you solve a either initial value problem or boundary value problem, an IVP or a BVP, you're going to get a solution or set of solutions denoted by y. That y, the solution, is called the response to our function, or the response to our system, rather. So here y, the solution y, is it's called the response function. And in fact, a lot of times people will leave off the word function. They'll just say the response. When we talk about a Green's function, what we're going to do is we're going to find a way to express the solution, the response function, in terms of the input function via what we call the Green's function. Okay, so how do we do that? Okay, well, let's say you solved one of these problems. You say, well, which one? For now, let's not worry about whether it's an initial value or a boundary value problem. Let's just look at this part. So let's say we're going to solve something like this. You say, well, without your conditions, this is just a second order non-homogeneous problem. I know how to solve that. I would find a complementary solution, and then I'd find a particular solution, and then add those together. Okay, so let's go through that. Let's say we were going to solve just this. Well, of course, we would start by finding the complementary solution, the solution to this equal to 0, or this equal to 0, same thing. Okay, so let's do that. Let the set y1, y2, let's have those be the fundamental solution set of this kind of problem. And of course, since it's the fundamental solution set, it's to the homogeneous problem. So we'll pretend that's 0. So the fundamental solution set of y double prime plus pxy prime plus qxy equals 0. Now, by variation of parameters, we can find that our particular solution, which we call y sub p, is equal to nothing more than y1, which is that first solution, times u of x, plus y2 times, I have two different u's, so I'll call this one u1 and I'll call this one u2 of x. This is just by variation of parameters. We can find u1 and u2 by using our Wronskian, our w1, and our w2. Well, we can actually we can do that, right? Where u1 is equal to the integral of w1 over w dx. But w1 was nothing more than you're going to take the, let's put this off to the side. You're going to take your Wronskian matrix, which looks like, what do we have here? We're going to have y1, y2, y1 prime, y2 prime. That's our Wronskian matrix. So then w1 would be, you would leave the second column alone, but the first column would be 0 and at the bottom f of x, your input function. Okay, so here w1 would be the determinant here. When you multiply these, you get 0. So really, you just have minus this. So you'd have minus y2 f of x divided by the Wronskian. Right? Oop. I've changed colors for no apparent reason, but okay, there we go. All right. Likewise, you could also say u2 is going to be the integral of w2 over w dx, which of course all that is you're going to take your Wronskian matrix and replace the second column now instead of the first one. So you'd get y1 and y1 prime. You'd get 0 and f of x. So here you would multiply these two to get your w2. That would be y1 f of x minus, and then this would be 0. So you'd end up with the integral of, and since I've already done that color, since I've already done it that colored with red, I'll do this one as well. So that would be y1 f of x over w dx. Let me try to be consistent with my color scheme there. So what that means is I can just take these two integrals and pop them in there. So y sub p is equal to, I've got y1, and I should write y1 of x, just to be clear that these are all functions of x. Times the integral right here of u1. Okay, now what we're going to do here, we're going to use the fundamental theorem of calculus. Here, we're going to write this first integral as the integral from x naught up to x of, I'm going to leave this alone here, I'm going to say minus y sub 2, but I'm going to write this as a function of t times f of t over, here I'm going to write this as w of t. You say, what does w of t mean? It just means you take your Wronskian, but instead of having these be functions of x, you write them as functions of t. So if this is e to the x and sine of x, then you would have e to the t and sine of t instead. It just means change the variable to t. Okay? dt plus, and then here my y2 is going to get multiplied by this integral, which again I'm going to rewrite as the integral from x naught to x of y1 of t. Let's see, y1 of t, f of t over w of t dt. And again, that is by the second fundamental theorem of calculus. second fundamental theorem of calculus. Okay, so now we look at this and say, well, hold on. That's an x, right? Yeah. That's a t, yeah? Yeah. And this integrals with respect to t, right? Right. So anything that doesn't have a t in there can be thought of as, for the purpose of this integral, as a constant. That includes this. This doesn't have a t in there. And what do we know about constants when it comes to integrals? We just move them in and out. So here we can rewrite this as the integral from x naught to x of, I'm going to go ahead and just multiply this one in here. Let's see, that'll be y1 times negative y2. Okay, so I'll say y1 of x, I'll put the negative in front, y2 of t, f of t, over wt of t, dt, plus, and then I'll do the same thing here. I can bring this in, and that's going to be the integral x naught up to x of, let's see, I'll do y1 of t, y2 of x, f of t divided by w of t dt. Now notice that both of these are integrals that have the same boundaries from x naught to x and with the same variable. And by linearity, that means I can take those integrals and just mush them together as one integral. So I can write this as the integral from x naught up to x of, now here f of t, I'm going to basically factor it out. Think of it as a common factor. So I'm going to have just this part here. I'm going to say minus y1 of, actually, you know what? Since this is positive, I'll write this one first. So I'll say positive y1 of t, y2 of x, minus y1 of x, y2 of t. They both have a same denominator, which is the Wronskian, with respect to t. So I'll write this w of t. And that whole thing is multiplied by f of t dt. Okay, so now what? Well, notice what you have. You now have a particular solution which is based entirely on the integral of the fundamental solution set. Remember, y1 and y2 were the solution to the homogeneous problem. Right? We can find those easily. It's non-homogeneous that's a problem. Non-homogeneous makes us jump through a bunch of hoops to find the particular solution. But here, what do we have? It's the integral of, well, the y1 and y2 are just the fundamental solution set. The Wronskian is found by the fundamental solution set and its derivatives. You say, well, how is that possible? Shouldn't the input function do something? Shouldn't the f of x do something? It does, but completely separate. We don't need to do anything with it. Everything comes from this being multiplied by a single function, which we can swap out at any time. So this guy right here, which comes entirely from the fundamental solution set, is basically the part that changes from one problem to another. F of t is just the input function. That's just that little function at the very end. So this right here can be used to find a particular solution with very little extra information. This is what we call the Green's function. So definition. Let's see here. Definition. Let y double prime plus pxy prime plus qxy equals 2f of x be a second order non-homogeneous linear ODE. Second order linear non-homogeneous ODE with a fundamental solution set y1, y2. In that case, we're going to find a Green's function. And notice that the Green's function is a function of two variables. It has x's and t's within it. So here we're going to write g of xt, it is a function of two variables, is equal to y1 of t, y2 of x, minus y1 of x, y2 of t, over the Wronskian of that w1, w2 with respect to t, like this. This is called the Green's function of that ODE. All right, so let's go ahead and see how this works. All right, let's take the following example. Let's go ahead and solve y double prime plus 3y prime plus 10y equals x squared. All right, so here we go. First, we're going to solve the homogeneous problem here. We're going to say, okay, pretend that's equal to 0. Y double prime plus 3y prime plus 10y equals to 0. Okay, that's nice and simple. We just have to find the auxiliary equation. We're going to write that auxiliary equation m squared plus 3m plus 10 equals 0. And then that factors. That factors is m plus, what do we got? Oh, I wrote the problem wrong. That should be a minus. I was about to say, that doesn't factor nicely, does it? Yeah, it's because I wrote it wrong. That should be a minus 10. There we go. That factors nicely now. That's going to be m plus 5, m minus 2. And so we have a solution, or we have two solutions rather, to the characteristic equation. We've got negative 5 and positive 2. m1 equals negative 5, m2 equals positive 2. So here we have a second order linear homogeneous ODE with constant coefficients. So we know that the fundamental solution set will be e to the this number t, and separately e to the this number t. And that's our fundamental solution set. Of x. I'm getting ahead of myself. We'll do t here in a little bit. Of x. Okay, so that is our fundamental solution set. Okay, so now what? Well, now we can create a Green's function. Here, our Green's function is going to be, you're going to take y1, which is this one right here, and you're going to write it in terms of t. And you say, oh, I got to do some algebra? No, literally just replace that with the letter t. That's e to the minus 5t. Okay? And then multiply it by y2 with respect to x, e to the 2x. Minus, now you take y1, now leave that one with respect to x, e to the minus 5x. And then take your y2 and write that with respect to t. So that'll be e to the 2t divided by, and then you're going to need your Wronskian. Okay, so let's go and do this off to the side here. My Wronskian is going to be the determinant of, I'm going to write those in the top row, e to the minus 5x, e to the 2x. But that Wronskian's got to be with respect to t. Okay, so when you write them in here, those are all with respect to t. That's the one annoying thing. You got to be very careful with what variables you're using. You have both of them, and they're used interchangeably, or not interchangeably. They're used reversibly in different parts. So here, that's my Wronskian with respect to t. I'm taking my two elements of my fundamental solution set with respect to t, and then taking their derivatives. So this would be minus 5 e to the minus 5t, and this would be 2e to the 2t. Taking the determinant, that's going to give me what? 2e to the negative 3t minus a negative 5, which would be plus 5, e to the negative 3t. So I end up with 2 plus 5, that'll give me 7e to the negative 3t. 7e to the negative 3t. And there's our Green's function. We can, of course, clean that up a little bit. When you multiply two things that have the same base, you just add their powers. When you divide something that has the same base, you just subtract the powers. All right, so right here, we can write this as, let's see, if I add these two, that'll be negative 5t plus 2t. But then I got to subtract this away. Subtracting a negative is the same as adding a positive. So I get negative 5t plus 3t is negative 2t plus 2x. So I get e to the negative 2t plus 2x minus, and then right here, again, subtracting is the same as adding the reciprocal here. Or sorry, I said that backwards. Dividing is the same as multiplying by the reciprocal. So here this would be a positive power. So I get negative 5x plus 5t. Negative 5x plus 5t over, and since I've already brought that into these two, I just get the 7 left over there. Okay? So now we're just about done, because we know that the solution to our non-homogeneous problem is going to be the complementary solution. Okay, well, we know the elements of the fundamental solution set, so it's just going to be C1 times the first one plus C2 times the second one plus, and now right here, we see that our particular solution is nothing more than the integral from x naught to x of our Green's function times the input function. You might wonder, what is x naught? In the next few examples, when we start seeing actual initial conditions, then the x naught will be from the initial conditions. But for now, we're just going to leave it as x naught. Just leave it as x naught. So here we're going to say, okay, that's going to be the integral from x naught up to x of, take your Green's function. That dividing by 7 is a constant, so I think I'll just pull that to the outside. I get 1/7 times e to the minus 2t plus 2x minus e to the minus 5x plus 5t times our input function x squared dx. Oh, sorry, dt. Let's see here. Oh, I made a mistake. It's supposed to be f of t. You see, that's why I said this is the one little annoying thing about using a Green's function, and that is because you switch back and forth between x and t in multiple occasions, it's really easy to make a mistake. I wish I could say I did that on purpose to highlight, oh, be careful, because look, you can make a mistake there. No, I legitimately just messed that up. Your input function here should be with respect to t. There we go. And you say, okay, so now what? Now we're done. You say, well, don't we need to integrate this? You could if you wanted to, but that's kind of the nice thing about using a Green's function. The Green's function gives you the solution in terms of an integral. Here, there's several reasons to leave it the way it is. One is the obvious, hey, I don't have to integrate. Isn't that nice? But another one, which is a little more subtle, but which is much more important from a mathematical standpoint, is look at where your input function lands. This is the only time you use it. This fundamental solution set gave you these two terms for the complementary solution. It gave you every one of these things for your Wronskian. It gave you every one of these functions in your Green's function. It gives you absolutely everything you see here except for x of t. And you say, okay, so let's say I changed my mind. And let's say over here, instead of saying x squared, I said this was x cubed. Well, then all I got to do is come over here and say, oh, that's a t cubed instead. And that's it. That's the correct solution now. Because if this doesn't change, none of this changes. If only this input function changes, only this little factor here changes. So one reason not to integrate is the obvious one. Hey, there's less work to do. But, well, since when have we shied away from a lot of work? No. The important part here, the big reason to leave this as it is because it allows you to change your input function by just changing this one term. Everything else remains the same. You say, so what? We never have to integrate this? Oh, well, no, I didn't exactly say that. I just said this is going to be the form of the solution that we care about here and now. In the event that you ever actually using this to do something in application, then of course you probably would want to integrate this. But hey, we already took Cal 2, we already took Cal 1, we know about integration. Let's not worry about that here. We're going to leave this in terms of a Green's function. So although we could integrate this, we're not going to. We leave it like that. You say, okay, that's nice. But I thought we were supposed to be dealing with these kinds of problems. We're supposed to be dealing with initial value or boundary value problems. There's no initial value. There's no boundary value problem here. We found a general solution. So how does this help with initial or boundary value problems? Well, our next theorem gives us an introduction to that. I say introduction because, well, we're actually going to have a few theorems that kind of stack together depending on what our needs are. So theorem, y sub p is equal to the integral from x naught up to x of the appropriate Green's function of our differential equation times the input function with respect to t. This is the solution to y double prime plus pxy prime plus qxy equals f of x, where y at x naught and y prime at x naught are both equal to 0. Okay. Notice this is an initial value problem. However, because these are the same number here you're plugging in, however, they're not as general as we usually allow. Right? Usually our initial value problem says you must plug in the same number, but the outcome may be different. Here, not only are the outcomes required to be the same, they're both required to be 0. You say, okay, well, that's a little bit inflexible, but I guess it's a start. Right? So here, we're going to have to find a way to make this a little more general so that we can solve just general initial value problems, but this is the start. Okay? So here, we're going to go ahead and give a quick example of this. We're going to go ahead and solve y double prime plus 9y equals sine squared of x, subject to the conditions that y at 0 is equal to y prime at 0 is equal to 0. Okay? These here are our initial conditions, and they're both evaluated at what we call x naught. X naught is what you're plugging into these initial conditions. So here x naught is equal to 0, and here our results are all 0 as well. Okay, so here we go. What we want is we want this initial value, this particular solution, which we get using our Green's function. All right, so let's give that a try. First of all, if we consider y double prime plus 9y equals 0, that has a characteristic equation, an auxiliary equation, m squared plus 9 equals 0, which has solutions m is equal to, or what have I got, 0 plus or minus 3i, which means that our fundamental solution set would be, let's see, it would be e to the 0 times cosine of 3x and e to the 0 sine of 3x, where 0 is the real part and 3 is the imaginary part. But since e to the 0 is equal to 1, well, then we can just say sine and cosine of 3x. So here we get a fundamental solution set of cosine 3x sine 3x, because the e to the 0 is just 1. And that is our fundamental solution set. Okay, so now that we have our fundamental solution sets, now we can find our Green's function and so our particular solution. Here, g of xt. Okay, we're going to take y1, that's this first one here, with respect to t. So that'll be what? Cosine of 3t. And then multiply it by y2, this time with respect to x. So sine of 3x. Minus, and now the exact same functions but with the variables reversed. We're now going to take cosine of 3x and then sine of 3t, which you may, some of the more observant of you who remember their trigonometry very well, you may recognize the sum and difference formulas for sine and cosine here. But if not, whatever, that is what it is there. And then we're going to divide by the Wronskian of these, which, if you note here, if I took these as y1 and y2, then the Wronskian would just be the determinant of, well, let's see, I would take the derivative of this one, which would be 3, let's see, derivative of cosine is negative sine of 3x. And then here the derivative of sine of 3x would be 3 cosine of 3x. So I would get 3 cosine of 3x minus a minus, which is plus 3 sine of 3x. Oh, that's just 3. Cosine squared minus sine squared is 1. Oh, but this is plus cosine squared. But this is 3 cosine squared plus 3 sine squared. Oh, that's going to equal to 3, isn't it? So our Green's function is 3. And so we get that our particular solution is going to be the integral from x naught to x. Now, before we said x naught, we're just going to leave it as x naught. But that's just because we didn't know what x naught was. We didn't have any initial conditions. Now we do. Look, x naught is 0. Right? X naught is whatever you're plugging into y and y prime. So your lower bound here is 0. If this was x, this is y at 1 and y prime at 1, remember, this has to be 0. These can be whatever number as long as they're the same. So here, whatever number this is, that's your bottom boundary. Your upper boundary is still the variable x. And then I've got my Green's function. I'll put the 1/3 in front. That way I don't have to write it all the way through. And then that's going to be 1/3 times cosine of 3t sine of 3t minus, that should be an x on that one, minus cosine of 3x sine of 3t times our input function, which is sine squared. We, again, want it with respect to t, not with the original x. So this would be times sine squared of t dt. And that's it. That would be our solution. This is our solution. Now, you could, of course, integrate this because now you know the bounds, and this is not that hard to do. You'd be using the, which one's this one? I guess that one's the difference formula for sine. So you'd end up with sine of 3t minus 3x. In any event, you could integrate this. This just uses some trig identities. If it is integrable, you might want to, but for the purposes of this section, the purposes of this class, we're going to leave things in their integral forms. All right. Okay, so now we see how, so this was our solution here that we're going to be looking at. So here we see how we can handle finding the solution to an initial value problem with any input function you could like. The restriction is you do have to have a very limited kind of input, a very limited kind of initial conditions. Now compare that to some problems we've seen in recent sections where we know how to solve initial value problems that are homogeneous. And again, that was pretty simple. Okay, so you can solve when this is simple and this is complicated. We did that before. And now in this section, we're seeing how to make it so that we can solve where this is complicated and this is simple. So we can kind of do one or the other, but not both. Well, turns out if you can do one and the other, you can do both. Here's our next technique. And in your textbooks, this is called, in most textbooks, this is called a theorem. Here I've been using the technique header for most things. However, in most books, this is called a theorem. So I'll go ahead and highlight that as well. Let I be an interval containing the initial value x naught over which the functions p of x, q of x, and f of x are all continuous. Now, if y sub h, and you say y sub h, what do you mean y sub h? It's kind of going to be the complementary solution, but it's going to differ ever so slightly. So we're going to call it y sub h. Here, h stands for homogeneous. We'll see that here in a moment. So if y sub h is the solution to y double prime plus pxy prime plus qxy equals 0 under the conditions that y at x naught equal to y naught and y prime at x naught is equal to y1. So here this is simple, and these can be whatever you want them to be. Y sub h is a solution to this initial value problem. It's called y sub h because it's the solution to the homogeneous initial value problem. You see, I thought solutions to homogeneous problems were y sub c. Yes, but usually when we say y sub c, we mean without the initial conditions. We mean just this part. So to highlight the fact that it is slightly different, that it's a homogeneous problem, but with the conditions, we change the symbol here. We'll call it y sub h. If you call it y sub c, whatever, it's kind of the same idea. But here we're trying to be extra careful to not get things confused. So if y sub h is the solution to this, and y sub p is the solution to what we just saw a moment ago, that is to say y double prime plus pxy prime plus qxy equals f of x, under the conditions that y at x naught and y prime at x naught are all equal to 0. So here, now this one's complicated, unlike before, and now these are simple, unlike before. Then the solution to the overall initial value problem, y double prime plus pxy prime plus qxy equals f of x. So now it could be complicated in the input function, subject to y at x naught equals y naught, and y prime at x naught equals y1. Now it can be complicated in the input function like this one, and it can be complicated in the initial conditions like this one. The solution to the one that has all those complications is just the sum of the solutions from the individual components above. That is to say, y is equal to y sub h plus y sub p. Here, these all have names. This is called the response of the system. This one here is the response to just the initial conditions. That's the one where the initial conditions are complicated, where this is simple. So this is the response to the initial conditions. And this y sub p is the one where the input function can change to something complicated. So this is called the response to the input function. So let's see an example of this. And really, these problems are not big problems. They're two little problems stuck together. All right, so let's go and give this a try here. For example, let's take a look at y double prime minus y equals the hyperbolic cosine. Like I said, this can be anything. Cosh of 2x, subject to the conditions that y at 0 equal to negative 1 and y prime at 0 equals to positive 2. All right, so here we go. First of all, we're going to go ahead and consider the case where we're going to have the initial conditions be this the way they are and the input function be 0. So that's going to be our y sub h. Okay, so we're going to go ahead and solve y double prime minus y equals 0, subject to y at 0 equals minus 1 and y prime at 0 equals 2. This is nice. We just find the auxiliary function. Here we're going to write the auxiliary function as m squared minus 1 equals 0. This is m plus 1m minus 1 equals 0. And so I have my two results, m1 equals negative 1 and m2 equals positive 1. Okay? So I get that the solution here is going to be what? E to the x plus e to the minus x with individual arbitrary coefficients. So here I get that y sub h is equal to c1 e to the minus x plus c sub 2 e to the positive x. Positive 1x, negative 1x, yeah? Oh, but we have initial conditions, so now we can plug those in. If this is y at h, then I need to find y prime at h because I have initial conditions for both of those. So y prime at h, sub h rather, is equal to, that's going to be negative c1 e to the minus x, and the derivative here is c2 e to the x. And now we can plug in 0 to both of those. So I get y sub h at 0. That's equal to c1 e to the 0 plus c2 e to the 0, which is just c1 plus c2, and that is supposed to equal to negative 1. Now, if I take y prime sub h at 0, then I get minus c1 e to the 0 plus c2 e to the 0. And since e to the 0 is 1, I get minus c1 plus c2, and that is supposed to give me 2. So now I take this small system here and solve. I could just add straight up and down. If I add these two up and down, these cancel out, and the c1 and c2 just cancel. The c1 and negative c1 just cancel. These double up. So I get 2c2 equals, and if I add these, I just get 1. So c2 is equal to half. Okay, but we know that c1 plus c2's got to equal to negative 1, or you can use the bottom one, same thing. And so c1 better equal to what? Negative 3 halves? That way negative 3 halves plus 1 half is negative 2 halves, or in other words, negative 1. Or the other way around, you could also say that's, put that in here, the negatives would cancel and you'd get 3 halves plus 1 half is 4 halves, which is 2. Either way, this is my result. So plugging those in here, I get that y sub h is equal to negative 3 halves e to the minus x plus 1 half e to the positive x. Okay, that's my y sub h. So now I want to find my y sub p, the response to my input function. And that I can do with the Green's function. Okay, so y sub p is going to equal to, let's see. Okay, so now I have to consider a different version of this problem. So let me put this little colon there. I'm going to solve, okay, so same problem, except now instead of making this 0 and leaving those the way they are, now I'll leave this the way it is and make those 0. Okay, so I'm going to solve y double prime minus y equals cosh of 2x, subject to the conditions that y at 0 and y prime at 0 are all 0. All right, so let's start by finding my Wronskian. My Wronskian is going to be, now I don't have to go and find my fundamental solution set again. I already have it from the last step. I've already got my fundamental solution set. It's going to be e to the minus t and e to the t. All right, so let's give that a try here. Now remember, your Wronskian for your Green's function needs to be in with respect to t. So even though these over here are with respect to x, I'm going to use those, but with respect to t. So I'm going to have e to the minus t, e to the t. And then the derivatives of those are negative e to the negative t and e to the t. Okay, so my Wronskian is going to be e to the 0. Oh, if I add those, yeah, that's just 1. Minus negative e to the 0, which is negative 1. So I just get a Wronskian of 2. Okay, that's nice. So now that I have my Wronskian, I can create my Green's function, g of xt. That's going to be, let's see, I need my y1 with respect to t here. So let's see, e to the minus t. And then my y2 with respect to x, e to the x, minus, and then same thing, but just switch the variables there. So now I want y1 with respect to x and y2 with respect to t. And then I'm going to divide the whole thing by my Wronskian, which is just the number 2. Okay. Here, since when you multiply two things with the same base, you just add their powers. That's going to be e to the x minus t minus e to the t minus x over 2, which you may recognize this. Anyone recognize this? This is sinh, because you can also write this as e to the x minus t minus e to the negative of x minus t over 2. So e to the something minus e to the minus something over 2, that's the hyperbolic sign of x minus t. So this is sinh of x minus t. Of course, if you don't remember that, you can always do everything in terms of exponentials. Either of these is fine, but, frankly, this is just less writing, isn't it? So I'm going to use this one. Okay, so let's see. So now I have my Green's function, so now I can find my y sub p. According to our previous theorem, y sub p is nothing more than the integral from our initial conditions x value here, so that's just this 0 here, Right? These right here are our x naught. And that's what this is right here. This is my x naught. So it's going to be 0 up to x of, I'm going to take my Green's function, which is just sinh of x minus t, times my input function with respect to t. So that'll be cosh of 2t. Cosh of 2t dt. And that's our y sub p. Now, up until now, I've been leaving these as they are in integral form. However, this one, looking at it, it's such a simple integration. I'm just going to go ahead and finish it. So here, this is sinh of something times cosh of something. That's the product. That's a product formula, right? If you may remember sine and cosine from trigonometry, sinh and cosh have the same product formula. So here, what you would do is you would get sinh of, or let me write that to the side, sinh of A times cosh of B is equal to half of sinh of the sum of those, A plus B, plus sinh of the difference of those, A minus B. The half would apply to everything there. So here what I would get is 1/2, and since that applies to everything, I'll just factor it out. 1/2 integral from 0 to x of sinh of, if I add these, I get negative x plus 2x is just positive x. So I get sinh of x plus t when I add those, plus sinh of, and then when I subtract them, I get I get x minus t minus 2t is x minus 3t dt. And now I can just integrate with respect to t. Let's see, with respect to t, the integral of sinh is cosh. Remember, unlike sine and cosine, there's no pluses or minuses there. So here this gives me 1/2. Let's see, I've got the integral of sinh is cosh of x plus t. And then over here, same thing, the integral of sinh is cosh of x minus 3t. But then because of that negative 3, since I'm integrating with respect to t, I need to divide by that coefficient. So just negative 1/3. I'll just place it there. Okay. And then I can even just distribute that 1/2 over to give me 1/2 cosh of x plus t minus half of a third. That'll be 1/6 cosh of x minus 3t. Like that. Oops, I forgot. I'm plugging in boundaries, aren't I? I'm not done yet. I put a little period there. I was like, I'm done. No, I'm not. So now I got to plug in x for my t's and then 0 for my t's and subtract. So I've got 1/2. If I plug in x, I've got cosh of x plus x is 2x minus 1/6 cosh of x minus 3x would be negative 2x. And then minus, okay, if I plug in zeros for t, I just get cosh of x. So I get minus half cosh of x. And then minus a minus would be plus 1/6 cosh of x again. Like that. And then, well, let's see. Cosh is an even function. So having cosh of 2x and cosh of negative 2x makes no difference. So here, I can get rid of the negative. And again, that's because cosh is even. And then right here, these are like terms. I can just combine them. So in the end, I get 1/2 cosh of 2x minus 1/6 cosh of 2x. 1/2 minus a 6 is a third cosh of 2x. And then right here, I've got minus half. Oh, that's be cosh. Minus half cosh of x plus a 6th cosh of x. That's minus a third cosh of x. And there we go. There's our particular solution. Like I said, normally you would just kind of stop here, but this one looked very simple because it just follows a simple identity. So I figured, well, what the heck, may as well finish that one off. But in any event, my result is going to be y equals, and remember, y is the solution not to either component, but to our original problem. That is to say, this problem here, y double prime plus 9y equals sine squared of x. Oh, that's not the right one. this one right here. Y double prime minus y equals cosh of 2x with the initial conditions y at 0 equals -1 and y prime at 0 equals 2. We got our y sub h. Over here we found our y sub p, and our result is just the sum of those two. So we end up that y is equal to y sub h plus y sub p, which will be, let's see, y sub h from before was minus 3/2 e to the minus x plus 1/2 e to the positive x plus, and then our particular solution here is 1/3 cosh of 2x minus 1/3 cosh of x, which I'm sure I could even clean up even further because I remember that cosh is written in terms of exponentials. So I bet you I could write this in terms of exponentials and combine further, but I think I've done enough damage here. I think I've done enough simplifying. That's sufficient for us. So this would be the solution to our problem here after finding the response to the initial our response to the input function, and separately the response to our initial conditions. We get our overall response of the system.